So, in the last video, we discussed polar and nonpolar bonds, and then after that, we discussed polar and nonpolar molecules. Well, before we go over coordinate covalent bonds and this weird saying that's likes dissolve likes, before we do that, let's do a brief summary and review of this very quick. Polar bonds. Polar bonds. Two nonmetals, if they're different nonmetals, they have different electronegativities and they will share unequally. So, polar bond, unequal sharing between two different nonmetals. All right, that's perfect. Nonpolar bonds. Going to be equal sharing, and the only example of equal sharing are these. So, nonpolar bonds are only found between the atoms of diatomic gases. N2, O2, F2, Cl2, Br2, I2, and H2. That's it. So, polar bonds, unequal sharing between two different nonmetals. Nonpolar bonds, equal sharing. Now, down here, a polar molecule. Really, it's supposed to be asymmetrical charge distribution. But for high school chemistry, let's just say if the molecule is asymmetrical shape, it's going to be a polar molecule. Okay, we're going to go over those later. The ones that we'll probably do will be this, H2O and HCl. Those two are polar molecules because they have asymmetric shapes. Nonpolar molecules have symmetrical shapes. The ones we're going to go over will be CO2 and C8H18. Those two are the ones. So these we're going to electron dot because they have something to do with likes dissolve likes, and if they're not likes, they won't dissolve. Okay, so polar, nonpolar bonds, polar, nonpolar molecules, and here we go into something called likes can only dissolve likes. Now, like we said in the last video, probably the most important molecule that you need to know to electron dot is this one. H2O. And we went over this before. O is 3.4 electronegative, H is 2.2, so O is really going to pull harder. But these are two nonmetals. If it's two nonmetals, it can't be ionic bond and it can't be metallic because there's no metal in there. So we are quickly going to electron dot this. Now watch. We're going to have O, pair, single, 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 pair. Then we're going to have the H's like that. And the H's electron, we're going to make an X, but they share them. O and H will share because one can't rip off the other, but O is stronger electronegative, so the pair is going to be closer to O. All right? Don't forget, that makes H slightly positive, slightly negative. And that's what O looks like. But what we didn't go over is these two positives are really kind of positive because their electron is much closer to O. So instead of a 90-degree angle between these H's, the H is spread out a little bit, and it's about 102 or 103 degree angle. So stick figure-wise, this is what a water molecule looks like. and then it has a pair and a pair. So, and remember, plus, plus, minus. So that's what a stick figure of a water molecule looks like. A little bit more than 90 degrees, about 102 or 103 degree angle. All right, now watch. The other thing is this. Any two nonmetals put together, if they're different, it's going to be polar bond. So these are polar bonds. This is a polar bond, and this is a polar bond. And then now we go. Is it symmetrical or asymmetrical? If I cut it this way, it looks the same on both sides. But if I cut it this way, it's asymmetrical. So now we know this. Water is asymmetrical. That means water is a polar molecule. Okay? All right, so that one's done. So we know this. H2O equals polar molecule. The next one we're going to go over is HCl. So here's Cl. And Cl is in group 17. Pair, single, 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 pair, pair. That's what chlorine looks like. It's got 3 pairs and 1 single. It's hooked to H. And once again, chlorine is stronger than hydrogen electron-wise, electronegativity-wise. So chlorine is going to pull hydrogen's electron over here. So this makes this slightly negative. It makes this slightly positive. So obviously HCl, 2 different nonmetals, it's going to be a polar bond because they share unequally. And now let's see if it's symmetrical or asymmetrical. Well, if I cut it like this, does that side look like that side? No. So HCl is asymmetrical, which means it's a polar molecule. Polar molecule. So both H2O and HCl are asymmetrical charge distribution or asymmetrical shape. They're both polar. Now, we're going to pick CO2. Well, CO2 are 2 nonmetals. So C and O have different electronegativities. So CO2, polar bonds. But watch what happens when you electron dot CO2. So we have C, and remember it's a little weird because it's 4 separate electrons, and then we have O2, we have an O here, and we have an O here, and they have single, single, pair, 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 single, single, pair, pair. Now watch. So when they get together, they have a pair of shared electrons there, a pair of shared electrons there, pair there, and a pair there. Now remember, O pulls harder. So these pairs would actually be closer to the O. So O would be slightly negative, the C would be slightly positive. And this is what CO2 looks like, but stick figure wise it looks like this. C, O, O. That's stick figure wise. Now, let's see. You know that if the O's pull harder, it's a polar bond. But let's see if it's symmetrical or asymmetrical. If I cut it this way, it looks the same on both sides. If I cut it this way, it looks the same on both sides. So now we know this. Now we know that CO2 is symmetrical. So if it's symmetrical, it's a non-polar molecule. All right, now the next one is a crazy one, C8H18. Now, I'm not going to electron dot it, but I'll show you the stick figure of C8H18. Well, first of all, C and H, 2 nonmetals, different electrodes, so it's going to be polar bonds. But now we have to see if the molecule is symmetrical or asymmetrical. So, watch. 1, 2, 3, 4, 5, 6, 7, 8. And then these are the hydrogens that I'm not going to put in. Remember, carbon has to have 4 bonds around it at all times. This is C8H18. You all know what it is. It's octane. Octane is gasoline. Okay? So watch. Let's cut it. This way looks the same on both sides. This way looks the same. Same. So what do we know about C8H18? It's symmetrical. So what that means is it's a nonpolar molecule. So, look what I have. H2O and HCl are asymmetrical. They are polar molecules. CO2 and CH18 are polar bonds, but they are symmetrical, so they're nonpolar molecules. So what does this have to do with likes dissolve likes? Easy. These two up on top, water and HCl, are both polar molecules. They can dissolve in each other. CO2 and octane, they are nonpolar molecules. They can dissolve in each other. Because likes dissolve likes. But what about this? Soft drink, Mountain Dew. Possibly one of the worst drinks you can drink. It's got brominated vegetable oil in it, which is a flame retardant, tons of sugar, got caffeine in it. I wouldn't touch the stuff. Anyhow, that's not what we're here for. This liquid is mostly H2O, okay? But there's fizz in it. The fizz is this, CO2. But now watch. H2O is a polar molecule, CO2 is a nonpolar. They don't mix. So how does the CO2 get in there? They put the CO2 in this liquid under tremendous pressure, and then they close the lid. The CO2 doesn't want to be in there because it's nonpolar. And you know what's going to happen. If you don't put the cap on tight, the CO2 will find a way to escape because it doesn't want to be in the polar water, right? So 2 ways to keep the fizz or the CO2 in. You got to keep the cap on tight, and you got to put it in someplace cold like a refrigerator. That'll help keep the CO2, which doesn't want to be in the water in the first place, in here. But eventually the CO2 will go away. So, the deal, likes dissolve likes. If you are some type of petroleum product like propane or butane or octane or petroleum jelly, they're all alike, they're all symmetrical. They dissolve each other. But think about this. Salad dressing, oil and water. It doesn't mix. Oil is this, which is a nonpolar molecule. Water is up on top. They don't mix. So the deal, likes dissolve likes. Polar molecules can dissolve polar molecules. Nonpolar molecules can dissolve nonpolar molecules. Okay? Okay, now that's likes dissolve likes. The next thing we're going to talk about is what the heck is a coordinate covalent bond. For short, I call coordinate covalent bond a CCB. CCB. Coordinate covalent bond. Now, I'm not going to give you the definition yet. I'm going to show you how one is made. Okay? And with the stuff that we just used. So, I'm going to wipe this out. We'll do a definition a little bit later on. So what we have is this. And I'm going to do stick figures. We have H2O. So H2O, remember, looks like this. So there's water. It's a polar molecule because it's asymmetrical. What we're going to do is we are going to bubble HCl into the water. Now, here's HCl. Now, there's water and there's HCl. They are both asymmetrical, so they're both polar molecules, which can dissolve in each other, likes dissolve likes. So here's the water molecule. We're bubbling HCl gas into the water. Now watch what happens. Remember, the chlorine is pretty strong and it's pulling the pair of shared electrons, this pair of shared electrons way over. So the H is kind of a strong H+. And that means, remember, H+ is only a bare proton. It needs 2 electrons to become stable. So here comes the HCl and it's floating over the water molecule. Well, something crazy happens. As the HCl floats over the water molecule, that H+ looks down and it sees a pair of unused electrons right there. So guess what happens? That H+ detaches itself from the HCl and sits right on top of that unshared pair of electrons. Pretty crazy. But now that H+ is totally satisfied because there are the 2 electrons it's sharing. And that is called a coordinate covalent bond. So, watch. Here's what a coordinate covalent bond looks like once that H+ jumps on. So now, watch. This is unequal sharing, unequal sharing. So both of these are polar bonds. Polar bond, polar bond. That's unequal sharing. But look at this one. You can tell it's unequal sharing because it's XO, XO. The X is from the hydrogen, the O is from the oxygen. But look at this one. This has OO, which means both electrons are from the oxygen. This hydrogen sits on top of that unused pair of electrons. So this, right there, is your coordinate covalent bond. Right there. And it makes this stuff, which is H3O plus. And H3O plus is called hydronium, but I don't care about that. That's a polyatomic ion. So once again, how can you tell if you got yourself a coordinate covalent bond? If they do an electron dot at you, all you got to do is wherever there's 2 O's or 2 X's, that's where the CCB is. That's not a CCB, that's XO. XO, but that's OO. That's from the same element. So, now here's the definition of a coordinate covalent bond. So, when one atom contributes or shares its unused pair of electrons to another atom, so this is kind of a long definition, but you just got to remember, one atom has an unused pair of electrons, and another atom needs 2 electrons that one that needs 2 electrons will jump right on top of that unused pair of electrons, and that's a coordinate covalent bond. So when one atom contributes or shares its unused pair of electrons to another atom that needs 2 electrons to become stable. And here's the cool part. So, look what this says. All polyatomic ions have at least 1 coordinate covalent bond. Some have 2. So what we're going to do now is I'm going to show you, and this gets pretty complicated, so you got to pay attention. I'm going to show you an electron dot of a polyatomic ion. So here we go. So this polyatomic ion I'm going to show you is this one. PO4 minus 3. PO4 minus 3 is the phosphate polyatomic ion. So, watch. Like I said, this is going to get complicated. So, I got P right here. P is in group 15, so it has 5 valence electrons, which is an S2P3, or pair, single, single, single. Now, that's P. The O looks like this. And there's 4 O's, so we got to have an O here, an O here, an O here, and an O here. Now, their electrons, they have 6 electrons. There's X, X, we have a pair, pair, X, X, pair, pair, X, X, pair, pair, X, X, pair, pair. Okay, now, that's what, it's going to get more complicated, but watch. Here's a shared pair. Here's a shared pair. Here's a shared pair. We don't know what's going on up there. But remember, the O is more electronegative, so the O is slightly negative. The P is slightly positive. So I'm going to go slightly positive. We're going to go negative, 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 negative. Now, if the O pulls harder, it's a polar bond. So look what I have. Polar bond there, polar bond there, and polar bond there. So I have 3 polar bonds, okay? Because O is pulling harder than P. But what the heck is going on up here? Well, here's what happens. This O needs 2 electrons. Well, there's 2 electrons. And what I said before, if you have an unshared pair of electrons and there's an atom that needs 2 electrons, it's going to jump on top. So what's going to happen is this X is going to slide up to here. And there'll be 2 X's there. And then look what I have right there. I have an unshared pair of electrons, and that O jumped right on top of it. That's my coordinate covalent bond. CCB. So that is my coordinate covalent bond. So I have 1 CCB and 3 polar bonds. Now, is everything satisfied? Well, let's take a look. We know that this oxygen is totally satisfied because it's got 1, 2, 3, 4, 5, it's got 8 around it. So that one's cool. This P is satisfied. 1, 2, 3, 4, 5, 6, 7, 8. That's perfect. What about this O? 1, 2, 3, 4, 5, 6, 7. So this O needs 1 more electron right there. Same thing with this O. It needs 1 right there. Same thing with this O. It needs one right here. So that O is satisfied, that P is satisfied, that O needs one, O needs one, O needs one. So how many electrons will it take to satisfy the phosphate polyatomic ion? 3. Oh, look. That's why it's PO4 minus 3. Because once that PO4 gets 3 more electrons, it's satisfied. So what could satisfy this polyatomic ion? A lot of stuff. Let's take something like this. Let's take lithium. Lithium's in group 1. It only got 1 electron to lose. So how could it satisfy that? Simple. I got 3 lithiums. So let's do that. Watch. Li plus, the electron goes right there. Li plus, that electron goes there. Li plus, that electron goes there. Now, up here, I just made this. Li3PO4. I just made lithium phosphate. But what about these bonds? The metal to the polyatomic ion. These 3 bonds are this. That's ionic, and that's ionic. So now I have crazy bonds in here. Unequal sharing, polar, polar, polar. Unshared pair of electrons gets shared, that's coordinate covalent bond. Lithium to the polyatomic ion is an ionic bond. And this thing, Li3PO4, looks like a salt. It's a crystalline solid, doesn't conduct electricity. So how in the world would I make that conduct electricity? I'd have to put it in water. But that's a different chapter. So, what I wanted to show you here is how coordinate covalent bonds are made. One atom has to have an unshared pair of electrons, and it shares it with another atom that needs 2. How can you tell if you got a CCB? That's the easiest thing in the world. It's not an XO shared pair. It's either OO or XX, which means the pair came from the same atom. Okay? So, what I'd like you to do for homework is this. I would like you to electron dot SO4 minus 2, show where the polar bonds are, show where the coordinate covalent bonds are, and then satisfy it by putting a metal on top of it. That's your homework. I hope you understand coordinate covalent bonds.